Hi everybody. First of all, if you're Chinese, happy Chinese New Year. But continuing from our last episode, we put some of our project on breadboard and had more work to do, and I've done just that. I've got quite a bit of this put on. Let me see if you can get the focus. Okay, so you can see quite a lot of stuff has been done on breadboard. We're going to walk through this a little bit, and but I ran into a little bit of trouble because I was actually going to power it off this transformer here. But as it turns out, this was underpowered. So I'm going to discuss that a little bit and see where we are with this thing. I'm going to have to order a new transformer. But let's just walk through this and maybe look at some of the software aspects of this project before we move on. Okay, let's get right into it. Okay, let's look at what we have here now. I've look at this, and you might remember this from the last video. And if you look carefully, you can see that I've actually duplicated the op-amp circuitry here. So we have two of these now, and this series of pins here, that's the ADS1115 ADC board. So I've got that down here. I hope this is focusing. I put the RTC here, the DS3231 RTC, that's down here now, and then the actual ESP8266 is over on this end. Now you remember the power supply is all in this section, so I put that the first thing I put down here is the ADC board because I didn't want to have any other devices on the bus in between. So I mean, reduce the interference. You can have all kinds of voltage drop down here, but I think the main section here, that's what I keep clean. So we've got a few tantalum caps here. Not sure if you can see, but there are actually a number of smaller 100 nanofarad or 0.1 microfarad decoupling caps all over the place. All right, these are also 2.2 microfarads, and here and at a number of places I've also put some decoupling up here just to make sure the signal is as clean as possible. And then I've marked out the I2C buses, the SDA, SCL, and where they're supposed to go. Connections are actually done on top of the board here. These diodes are the clamping diodes as well as the rectification diodes. And then I put a big 1000 microfarad here for the smoothing capacitor before the regulator. Regulator is down here. Okay, that's good for up to 500 milliamperes according to the data sheet. And then this little thin enamel wire here, that wire actually is signaling the conversion, the completion of conversion, so that the MCU knows that conversion is done. Okay, now this end here is supposed to be the transformer, but if you look at this, I'm not sure how close I can get with this thing, but you can see that this is actually 0.75 VA, right? So it's a 6 volt 0.75 VA. And what that means is that at 6 volts, this thing is rated to deliver 125 milliamps, right? So we're going to see, can we power this board with 6 volt 125 milliamps? So we're going to do that just right now. So you can see I've got this whole thing set up here now with our bench power supply, and I've got this thing set up to 6 volts at 100, and let's make it 125 milliamperes. Okay, so that's what this will get you, right? This will get you 0.75 VA. That's 175 milliamperes. So we're going to power this up and see if this whole thing will run, because if this works, then the transformer is good. Okay, so here we go. I'm going to turn on the power output now. Okay, you can see that it's gone into current limit mode. The voltage has dropped to 126. Okay, so this is not working. Okay, the lights are not coming on, and let's try that again. Okay, so this is not working. Let's bump up the current a little bit. Let's make it 180 volts. Okay, just see, maybe we can, let's make 170. Okay, that works. Okay, so 175 is not, but even at this 170 milliamps, you can see this light comes on, but this light here, it doesn't come on. So what it's telling me is that the ESP8266 is not booting up. This is not working. It's got enough power to get the RTC going, but for whatever reason this guy is not working. Let's just bump it up even more. Let's just see, let's make it 266. Now this is I'm going to replace this with a different transformer with 266 milliamp capability. Let's see what happens if we do that. Okay, I'm not sure if you can see this, but if you look, you can see that the LED here is now on. It's not terribly bright. I'm going to turn off this light so you can see that maybe a little bit better. So let's turn this off again, right? So if I turn this on, let me just make a quick adjustment here, just so that it looks a little bit better, right? Okay, if I turn this on, this light comes on, so that's great. That's exactly what we want, right? If we go back to 170, let's say, let's make 125, okay? 125, just to be being a little bit OCD here. Okay, that 125. You see the LED flash for a second and then it goes off. Even if I were to increase this to 100 and let's say 180 milliamps, you can see that LED comes on, the RTC LED comes on, but it doesn't boot. So in short, we actually we're going to need a beefier transformer because that 0.75 VA thing is just not going to cut. I've been spending a little bit of time working through the code as well. There were some problems in the code, namely with the SQL connector library, and it was causing all kinds of resets. And turns out that I had to modify the library because it was having some conflicts with the code. Now I've made a couple of changes here. In the past, I would trigger an interrupt every how many milliseconds to read the ADC, and then you'll wait for the conversion to finish. You'll grab the reading and it'll come back. But now I've changed that completely. What I have now is basically two different interrupts. The first interrupt gets triggered on the clock. So after a certain amount of time, this sampler ISR2 gets called. What it basically does, it begins the conversion. So you have, well, it toggles the LED. This bit here toggles the LED. And then it will actually begin the conversion, right? So it goes down to, well, the toggling of the LED, I might say. There's a little bit of, I guess, timing because these conversions are happening so quickly. The interrupts are happening so quickly you can't see it, so I have to slow it down by some factor. But in any case, it calls this thing called start ADS 1115. What this basically does is it simply sends the beginning part of the conversion, right? So it sends this whole packet of 3 bytes, actually should be 4 bytes, and it configures the thing and it starts it off in a single shot, some configuration setting with a particular channel in mind, and then you come back, you return from the interrupt so that your main loop and everything else can keep going. And when the conversion is finished, I've set up a second interrupt which actually goes on the ready pin, right? And I had some trouble with that because it turns out that the interrupt on the pin can only work if you're using GPIO, well, anything but GPIO 16, and as luck would have it, I was using GPIO 16, so that kept me puzzled for a long time. Then I found out, you had to use something else and it started working. So what happens is when the conversion is complete, it calls this function here. It comes in, right? So the first thing it does is checks this, that's sort of like a state machine there. It tells you which state, because after the first conversion is complete, case 1, the ISR state keeps the state. Well, what it does is it reads the results of the previous conversion, right? It calls finish read, reads that into the, and then it begins the next conversion, which is for the amperes, right? So you actually need to make 2 sets of conversions, and it changes the state, and then the next time it comes around, it goes into this state 2, and it reads that, and if it checks whether we've read 1 minute's worth, which is actually here you go, right? This watt. So watt count.
So WAVG is basically telling you how many conversions sets you need to make for 1 minute, and the count simply counts the number of conversion. And if you have done 1 minute worth of conversion, it will aggregate all that stuff. It will flag the main loop that, you know, there's data ready and to do some stuff. So the difference between this and the earlier design I had was that this wouldn't hold up, this particular scheme wouldn't hold up the CPU during while it's waiting for the conversion to end, and that could take quite a lot of time, right? I mean, you think about it, conversions will take, I mean, in order of milliseconds, but you, with this many conversions going on, you waste a lot of time waiting. So this releases the MCU so that, you know, you can do other stuff. I did make other changes to the code as well. I bumped up the speed from 80 megahertz to 160 megahertz. So hopefully everything is running more quickly. I had to rewrite the code. I'm using the BRZO I2C library, so I had to rewrite the code, you know, from this, which was the original. You know, there's this whole thing about waiting for the conversion to finish here. So I kind of got rid of that. There's a whole bunch of other stuff I did, right? Namely, so one of the things I did down here was that I added a telnet server. The reason for this is because, you know, once I get this, I suppose when I get this unit away from the computer and running, I couldn't monitor the serial output from the serial port that you normally would be using. So I put in a telnet client, so that telnet server basically, so that I can call in and I can telnet to the machine and get some feedback and find out what's happening with the machine, right? Also help during development, because then, you know, I can monitor stuff as I play with it. All right, so I added that. So this whole section here, you know, initializes the session. You know, it echoes some stuff. It doesn't do anything actually. It doesn't really do anything here. And then every 200 milliseconds, every 2 seconds, it will just print some data down here. Okay, so that's something I did down here. I also changed the clock. Okay, well, I noticed that the timing loops are not very accurate. So every now and then it sort of loses time or gains time. So what I have is this whole section here. This is if that data is ready. What this does is it checks if I've got average data. Now if data is ready, then it will construct the MySQL string to be sent to the server, right, which is actually done with this write MySQL, something I wrote in my code above. But here's the bit here that I'm a little bit more interested. So it checks the time, right? Usually I'll synchronize everything with 0 seconds, a transition between 59 seconds to 0 seconds. It checks if I'm still in sync. If for some reason the sample is coming in at 59 seconds or 1 second, this will actually add or remove samples from WAVG. You remember earlier, it either adds or remove 1 or 2 samples just to adjust the time back a little bit. So it keeps it, well, I guess the assumption is the RTC, the real-time clock, is accurate, and it keeps this synchronized more or less with RTC. So that's what I did. So fixing the main thing I spent quite a few days doing was really fixing the SQL library, and that was causing all kinds of resets. That was nothing to do with my code. And by the way, I had this problem with my other projects as well. So that really helped. And then there was some random hardware watchdog resets, which I basically needed to add some yield, which feeds the watchdog so that it doesn't time out, right? So with this in mind, I actually now have this thing running like this, and I'm going to reset the thing once again. You're looking at some of the results. I'm going to reset it right now. Okay, so this is what it looks like when it gets reset. You can see at the bottom here, this some garbage here. It's just the result of the reset. You have the text coming up. It grabs the IP from the DHCP server, connects, and it grabs the time from the NTP server somewhere. I can't remember which one, and you know, it checks actually if there's a real-time clock, in which case, in my case, there is a real-time clock. It can work without this, but since I have it, it makes sure the real-time clock and the NTP time kind of lines up. So in case one fails, it has a backup, right? And then it starts the telnet client, and then what it does here is it waits until you get the transition from 59 seconds to 0 seconds. So when that happens, it begins the sampling, right? So it usually will wait a little bit here. So over here it's 52, 51 seconds, so 1 second difference here. It waits about 8 seconds, and then it begins the conversion, right? So this now will take one sample every minute. Okay, so 1 minute's up. You can see there's a little bit of time differential. Here's 59 seconds. So internally, it's going to make some adjustments so that the next sample comes up at, hopefully, you know, in 1 minute's time, it'll come up at 0. So I'm going to put this one side because that's actually quite nice. I'm going to bring up a telnet server now. Let's see where we are with this. Okay, so let's use putty minus telnet 192.168.1.143, which is the IP that we had there. So this, you can see it kicks up this thing here. All right, so let's put this here side by side. Okay, so now you have this telnet loop that's going every 2 seconds. It just prints out whatever the data is. Now I have everything strapped down to 0, and you notice that even though the input is at 0, there's a little bit of this is the raw, this bit here, that's the raw ADC output, right? So this is the interpreted output. So there's some stuff going on there, probably some noise. I may have to do some characterization or output, check the linearity, and maybe offset that bit from the output eventually. We'll do that in the next video, but for now you'll notice that we have this here. So the next loop, it actually extended the timing a little bit so that we are back on 0 seconds, right? So this will keep going. Now in the past, with all those problems, it will randomly hang after an hour, 2 hours, sometimes 3 hours, and it was quite difficult to figure out what was going on. But now I'm really happy. This arrangement has run for quite a long time, and it has not crashed. And you know, you need to make sure it doesn't crash, because this is a long-term logging project. So I'm going to just basically end this video right here. In our next video, we're going to do some measurements and checking for linearity, and maybe looking at the current sensor that has come in, right? So we'll do a bit more interesting measurement stuff in the next video. All right, see y'all.